Today, we're going to be talking about geometric series, which are a very interesting topic of mathematics. They sort of follow off of what we've been doing with infinity because one very interesting sort of avenue of geometric series is the infinite geometric series where we have an infinite number of terms. And you'll see, interestingly enough, we have some pretty cool formulas where we can calculate things like the sum of an infinite geometric series, which may seem kind of crazy because how could you find the sum of an infinite number of terms? But you'll see how we do that in just a moment. So first, let's just start off with a sort of a definition of a geometric series. Basically, if we think of a geometric sequence as a bunch of terms, we start with a first term, we can call that a sub 1, and how we get the preceding terms is we multiply by a common ratio, where we can just call that r. So our next term is just going to be a sub 1 times r. From there, we can just keep multiplying the previous term by r again, this common ratio. So the next term is a sub 1 times r squared, and so on, and we would have as many terms as we want. If we think of this as the first term, second, third, then you'll see that in general, we can write the nth term as a sub 1 times r to the n minus 1. A series, as I mentioned, of geometric terms is the sum of the terms. So what I just showed was a sequence. However, we can also use a geometric series where we add up all the terms, meaning the geometric series of what I just wrote out would be the sum a sub 1 plus a sub 1 times r plus a sub 1 times r squared, and so on, until we add a sub 1 times r to the n. Now we can look at a proof of the formula for calculating the sum of a geometric series when we have a finite number of terms, let's say n. So we can write the sum of a geometric series simpler by just writing this big capital sigma, which is a Greek letter that means sum. Back down here in the bottom, we like to write what we call our index, so we can choose any letter, let's say k. We start at 1 and we're going to go up to n, meaning we start with our first term is going to be called the first term and our last term is going to be the nth term. In the stomach right here of this Greek letter, sigma, which we'll write to the right, is going to be the definition of each term in general, meaning we can write each term as a times r to the k minus 1, similar to what I said up here. It's just instead of n, we're using k. But you'll see that k goes to n. It starts at 1, and it goes up to n because we have n terms. So we know that this big sigma means sum. So it equals a sub 1 plus a sub 1 times r plus a sub 1 times r squared plus dot 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 a times, or a sub 1 times r to the n minus 1. Now we want to prove our formula, which you'll see at the end is a minus a times r to the n all over 1 minus r. So our first step is we're going to multiply both sides of this equation by 1 minus r. So on the left, we're going to have 1 minus r times this big sigma equals 1 minus r, 1 minus r times our sum, in parentheses, so now from here, we're going to do a little bit of rearranging. So I just moved what we had up to the top to give us more room. So now what we're going to do is on the right, we're going to multiply out this parentheses. So we leave the left the same, and on the right, you'll see that if we multiply out the parentheses, we get this, a sub 1 times a sub 1 times r plus dot 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 plus a sub 1 times r to the n minus 1. Then minus, because now we're going to have to do this right here, we have this minus r, and we have to multiply it by this whole parentheses. So now we're going to have a big minus sign, and we're going to have minus a sub 1 times r sub 1 times r to the 1 minus a sub 1 times r squared minus dot 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 minus a sub 1 times r to the n. Because remember that last term in this parentheses right here is a sub 1 times r to the n minus 1. So when we multiply it by r, we're going to get that last term to be a sub 1 times r to the n, because we multiplied by 1 more r. Now, you might notice that we can cancel a bunch of these terms. You see how we have this term is the same, and in here we're going to have all these are going to cancel out, as well as this term. So actually, what we're left with is a sub 1 minus a sub 1 times r to the n. But on the left, we have 1 minus r times our big sigma, which is just our sum. And if we divide by 1 minus r, put it on the right side, we get our sum of this sequence equals a sub 1 minus a sub 1 times r to the n over 1 minus r. So what that means is if you had, let's say, a sequence, geometric sequence, 1, 2, 4, 8. So here the common ratio is 2, right? Because we're multiplying by 2 to get our new term. And let's say it went up to 64. You're not going to want to add all those numbers up. So what you'll do is you'll plug it into our formula. So what you'll do is you'll count up the number of terms. So we have, that's our first term, third term, fourth term. 16 would be our fifth term. 32 would be our sixth term. And 64 would be our seventh term. So we've n equals 7. So when we plug into our big sum formula, we're going to get the big sum. The sigma means sum, remember. A sub 1 is just the first term. That's 1. 1 minus 1 times 2, because our ratio is 2, remember, we multiply by 2, to the, remember I said 7, divided by 1 minus 2. And if we simplify that, which would really just be 1 minus 2 to the 7th over negative 1, we're going to get the sum of this sequence if we added up all these terms. So that's a pretty cool formula, and it's super important. Now we're going to do a similar formula, but for when we don't have n terms. Instead, we have an infinite amount of terms. So now we're going to look at this infinite series. We have an infinite number of terms. They never end. There's an infinite amount, and we're going to find the sum of that sequence. So here I've written our sigma. We have our index. It starts at 1, the first term, and it goes up to infinity. So it's a little crazy to think about, but it actually equals, and we'll prove this, the first term, a sub 1, divided by 1 minus r. That's simple, where r is that common ratio that we talked about. However, there's one catch. This only works when your ratio is less than 1, the absolute value, that is. Meaning you could have a ratio of minus 1/2, it would still work. Ratio of 1/2, it just has to be less than 1, that absolute value. Meaning on an interval, we could write it as from negative 1 to 1, meaning 1 is not included, but anything that's less than 1 and greater than -1 works. So, without further ado, let's just start off with a quick understanding of why it's even possible to calculate an infinite sum. Because let's take that sum that I showed you just now that we used as an example, where we had 1, 2, 4, 8, 16, and so on. Basically, it was just the powers of 2, right? We multiplied each previous term by 2, and we got our new term. If we were going to add up all those terms, an infinite amount, it would obviously be infinity, right? And the reason that we can calculate the sum for some series is because of this green little bubble that I drew. Here, r equals 2. That's greater than 1. And you'll notice that if we write as a limit, which we talked about a little in one of our Zoom sessions, as n approaches infinity, a sub n equals 0. When the absolute value of r is less than 1. And the reason that this is true is because remember that a sub n we can write as a sub 1 times r to the n minus 1. When r is less than 1, that means that we can actually write a sub n as a fraction, essentially, where we have on the denominator a very large number that keeps getting bigger and bigger and bigger as n increases, which means as n approaches infinity, that term is going to equal 0. So for instance, let's just say that r equals 1/2. If we have a fraction then where when r is 1/2, we can write a sub n as a sub 1 over 2 to the n minus 1. Because essentially that's the same as writing a sub 1 times 1/2 to the n minus 1. But when n is getting bigger, this denominator is getting bigger and bigger and bigger and bigger. And essentially, it's going to go straight to 0 because a sub 1 isn't changing. It's staying the same. And if you have a sub 1 over a super, super big number, that's going to approach 0, which is why we write the limit as n approaches infinity, it's going to go to 0. And that's the reasoning behind eventually our sum, we say, is going to the sequence is going to converge. And that's why a sum can be calculated. Whereas when r is greater than 1, this is not true. Because a sub 1 times, let's say it was 2r, r equals 2 to the n minus 1, never is this getting to 0. Because that's just getting bigger and bigger and bigger. And that's why we can find the sum when r is less than, the absolute value of r is less than 1. So now let's prove this formula for when absolute value of r is less than 1 and we have an infinite series. So let's call S capital our sum. So S capital equals a sub 1 plus a sub 1 times r plus a sub 1 times r squared plus an infinite amount of terms. Never ends. We can factor out an r. At first it doesn't seem like that because there's no r in this first term. Although all the other terms have r, you would think that we couldn't factor out an r from this first term. However, we can write it as this. If we take r out, we can write a sub 1 times r to the minus 1. Because what happens when we multiply that? R times a sub 1 to the times r to the minus 1. Those r's cancel, and we're left with a sub 1, which we started with. Then the second term you see is a sub 1, because when we multiply r times a sub 1, we get our second term, and so on. So we actually can factor out that r. And remember that we have an infinite amount of terms. Okay, so now is the really tricky part, but it's actually super cool if you notice it. So I'm going to give you a couple seconds to see if you can recognize what that is. So what that is, if you notice in line 1, right here, this is s. That's our infinite sum. We can replace that then with s. So we have s equals r times, open parentheses, a sub 1 times r to the minus 1 plus s. Now, if we multiply out the parentheses, remember what I said about when we multiply these, we get a sub 1, right? Because r times r to the minus 1 is 1. So we just have a sub 1 plus r times s. Now, we can bring s to the left, that r times s I mean. So we have s times, or minus r times s equals a sub 1. Now we can factor out s. We get 1 minus r equals a sub 1. And from there, you guys can figure this out. We get s equals a sub 1 over 1 minus r, just like what we said at the beginning. Pretty cool, right? So let's do some practice with what we just learned. Let's say we have a sum that's 7, oops, that's the highlighter. That's 7 plus 7/3 plus 7/9 plus 7/27, and it's an infinite term. As you might be able to see, our common ratio is 1/3, which is less than 1, because each time we're multiplying by 1/3 to get our new term. So based on our formula, that infinite sum of our series equals a sub 1 is 7. That means just the first term is what a sub 1 is. Divided by 1 minus r is 1/3. So it equals 7 over 2/3, which equals, we can flip that bottom fraction, because when we divide by a fraction, we can actually flip it over and multiply by it. So it's actually 7 times 3/2, which equals 21 over 2. One interesting application, or not application, but kind of a visual proof of that infinite series sum is, let's say we have a square. This sort of shows the idea that an infinite sum can actually converge and equal a real number. It's not going to always be infinity. Let's say we have this square, right? And it's 1 by 1. So each side length is 1. Let's cut it in half. And then let's cut what we cut in half in half. And let's cut what we cut in half in half in half, and so on. And you'll see that we keep cutting our halves in half. And let's add up all those pieces. So we have 1/2 of the square here, 1/4 here, 1/8 is this part right here, and so on. If we add all those pieces up, we know that it equals 1 because it's inside this 1 by 1 square. So that's equivalent to saying 1/2 plus 1/4 plus 1/8 plus dot 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 equals 1. And we can show this because let's use our little formula. A sub 1 equals 1/2 and r equals 1/2. So 1/2 over 1 minus 1/2 equals 1/2 over 1/2, which equals 1. So our formula is right. And we have proved that infinite sums, only when, as we showed with the limit, r is less than 1, can be equal to a number, not infinity, which is a little unintuitive because you would think, well, if you add an infinite number of something, that it would actually be infinity, which is not the case. One last thing that we're going to show to close out the video is when r is negative. Because remember, the absolute value of r can be less than 1. Meaning you could have negative 1/4 as your ratio, or negative 1/3. So let's do a quick example. Let's say that we have r equals, let's say, negative 2/3. So that's less than 1, its absolute value. And let's say that our first term, a sub 1, equals, let's just say, 1. So our sequence would be 1 minus 2/3, 4/9 minus 8/27, and so on. And if it's an infinite sequence, so we have an infinite number of terms, let's find the sum of that series. So first term is 1. So in the numerator, we're going to have 1. The denominator, we're going to put negative 2/3 because r is negative. And we're going to get 1 over 1 plus 2/3 because 2 negatives make a positive. We get 1 over 5/3. And remember, fraction on the bottom, we can flip it and multiply, so it's 1 times 3/5, which of course equals 3/5. So that just shows a quick example that when r is negative, it's still pretty simple. This formula is incredibly useful and also incredibly interesting, having this infinite amount of terms that actually, when we add them up, they can converge to a number that's not infinity, which is, like I said, kind of non-intuitive. But there's something, these series are super common in mathematics, especially competitive mathematics, so they're worth practicing and sort of getting a feel for, because at first it might be a little confusing, I'm sure. And as well, we'll make a video eventually on arithmetic series, where instead of multiplying to find the next term, you add. So for instance, you'd have 1, 3, 5, 7, 9. That's an arithmetic sequence where we add 2 each time. And you'll see that arithmetic sequences are a little different. The sum of an arithmetic sequence has a different formula, as you can imagine, but like geometric series and sequences, super important and super interesting. So yeah, stay tuned for that video. Feel free to send us any questions that you have over this topic, and attend the Zoom meetings that we hold each week, where we go more into depth, answer questions, do more examples. But for now, that's the end of this video. I hope you enjoyed. I hope it sort of made some sense, especially for some of you where this might be brand new. And thank you for listening. Bye. Then